All right, in this video, we're looking at a kinetics topic, reaction mechanisms, and potential energy diagrams. In this first question, we're talking about a household medication, hydrogen peroxide, which is used as an antiseptic. You may have used it at home if you had a cut or a small wound. It bubbles when it's put on your cut. It stings a little bit as well. The bubbling is due to the production of oxygen gas. As the hydrogen peroxide, H2O2, decomposes. It also produces water. It can happen by itself, that decomposition reaction. In fact, it's catalyzed by light. So when you buy it, it's often found in a dark brown bottle to prevent light from reaching the chemicals inside. But there are various things that can be catalysts for this reaction. They speed up the reaction. One of those catalysts is hydrobromic acid, HBr. When there's hydrobromic acid present, the decomposition occurs by a two-step reaction mechanism shown here, step 1 and step 2. So we're asked in part A to write the balanced equation for the overall reaction in the mechanism. To do that, you look at the two steps and you cancel out anything in the mechanism that appears as a reactant in one step and a product in the other step. For example, the HBRs are reactants in the first step, the two of them, and they're products in the second step, so we can cancel those out. Also, the bromine, Br2, is a product in the first step, but it's a reactant in the second step, so we can cross it out as well. That looks like everything that can be crossed out, and whatever's left in the reaction qualifies as the overall reaction. So on the left, we have two H2O2s, so we can write 2 H2O2, and that's the only thing left as reactants. So it becomes, as it decomposes, on the right, we have two waters, and we also have an oxygen. So 2 H2Os plus O2. There's the overall reaction. Now, in that mechanism, there were intermediates and there were also a catalyst. The intermediates were things that are produced in an early step, so in this case, produced in step 1, but then they were used up as a reactant in a later step, in this case, step 2. So by that definition, we can see the bromine was a product in the first step, and then it was a reactant in the second step. So bromine qualified as an intermediate, Br2. So it'll be found on the right-hand side in an early step of the mechanism, and then later on the left-hand side, and it always cancels out. A catalyst is something that we know speeds up a reaction by changing the mechanism and lowering the activation energy. And we know part of the definition of a catalyst is that it doesn't get used up. A catalyst in some ways can be thought of as the opposite of an intermediate, in that you will find it first as a reactant. So in the first step, the HBr was a reactant. And then later in the mechanism, in a later step, it'll be produced again as a product. So in this case, the HBr was produced in step 2. So the HBr qualifies as a catalyst. It was a reactant in the first step and a product in the later step. Because it's produced again, it can go on to catalyze further reactions. Now, there are two different broad categories of catalysts. They can be homogeneous or they can be heterogeneous. If they're homogeneous, it means the catalyst is in the same phase, solids, liquids, gases, aqueous, as the other reactants in the reaction. So when we look up at the mechanism, notice that the HBr was aqueous, while the H2O2 that it was reacting with was also aqueous. So because the catalyst there was the same phase as the other reactant that it was working with, this was a homogeneous catalyst. If the catalyst, homogeneous, if the catalyst were a different phase, so maybe we were using a solid catalyst with the aqueous hydrogen peroxide, then it would have been a heterogeneous catalyst. The last question asks us to explain how a small amount of catalyst can catalyze the decomposition of large numbers of hydrogen peroxide molecules. I won't write out my full answer to that, but the simple answer is that because the catalyst is produced again at the end of the mechanism, in this case in step 2, it's able to go on and react again. It can react with more hydrogen peroxide after that. So small amounts of HBr can end up decomposing quite a few H2O2 molecules. And the last question, write a simple definition of reaction mechanism. Well, we've implied it in our discussion so far. The idea that the reaction for the decomposition of H2O2 occurred by two different steps, that was a description of the reaction mechanism. So a mechanism is the series of steps or the series of collisions involved in a chemical reaction. Here we're looking at the same reaction, but this time represented as a potential energy diagram. You can see in the diagram that the large curve here on the outside represents the uncatalyzed potential energy diagram. There was only one hill, so it was a one-step uncatalyzed reaction. It's also a pretty tall hill, so it has a very large activation energy. If we think of the activation energy, the difference in energy from the reactants to the activated complex at the top of that hill. So it was a pretty slow reaction because it had a large EA. When you added the catalyst, then the reaction's mechanism changed. Instead of being a single-step process, it ended up following this two-step process. And in that two-step process, you can see the activation energy for both steps was smaller than the activation energy in the original uncatalyzed reaction. So part A says, what was the effect of the catalyst on the EA of the original reaction? Well, you can see in the diagram that the activation energy was lowered by the addition of a catalyst. What about the effect of the catalyst in part B on the heat of reaction, delta H? Well, if we look at the diagram, the delta H, the heat of reaction, is the difference in energy between the reactant particles and the final product particles, which are over here. Notice in the original uncatalyzed reaction, those energies are the same as the energies in the catalyzed reaction. So the delta H, the heat of reaction for the overall process, would not have changed. So the delta H of the overall reaction is the same in the original uncatalyzed reaction as it is in the catalyzed reaction. Catalysts do not affect the delta H of the overall process. And lastly, we're asked which of the steps in the catalyzed reaction was the rate determining step. The rate determining step, of course, is the slowest step in the mechanism, so it would be the step with the largest activation energy. So in this diagram, the first step had an EA here, so it was a pretty small EA, and in the second step, the EA is here. Remember, the EA is the difference from where that step began to the formation of the activated complex in that step. So for step 1, it's the difference that I've just highlighted. In step 2, we begin here in the diagram and we move up to the top of the hill here where its activated complex is formed. So step 2 had a larger EA. Because step 2 has a larger EA, the step 2 would be the slower step. And step 2 would be the rate determining step. In this third question, we're looking at the destruction of ozone catalyzed by CFCs high up in the atmosphere. It occurs by a two-step mechanism. I'm going to zoom in a bit so we can see that a bit better. So here's the two-step mechanism. Step 1, the ozone reacts with a chlorine atom, a chlorine radical, high up in the atmosphere. In step 2, the ClO that was produced in step 1 reacts with more ozone as well. So the O3 is ozone. It says write the equation for the overall reaction. If you want, you can pause the video and try that yourself. So like we did earlier, we're going to cross out things that appear on both sides of the reaction. So we can cross out the ClO. It was produced in step 1 and used up in step 2. We can also cross out the Cl. It was a reactant in step 1 and Cl is a product in step 2. The things that appear on both sides of the mechanism can be canceled out. Whatever we haven't canceled out is the overall reaction. So in this case, we have 2 ozone molecules, one from step 1 and one from step 2, and that becomes 3 oxygen molecules, one from step 1 and 2 from step 2. Identify the catalyst and to state whether it was heterogeneous or homogeneous. And remember that a catalyst is a substance that begins as a reactant, so it's on the left side early in the mechanism, and then later it comes back as a product. So by that definition, the Cl was a reactant in step 1, and then it was a product in step 2, so the Cl would be the catalyst. Whether it was homogeneous or heterogeneous, we look at its phase. So the Cl in step 1 was gaseous, a gas, and it was reacting with ozone, which was also a gas. Because they had the same phases, this was a homogeneous catalyst. So notice we're just comparing the phase of the catalyst with the phase of the other reactants in that step. Identify the intermediate in the mechanism. Well, the intermediate is something that is produced in an early step, and then later it's consumed. It's a reactant in a later step. So the ClO was produced in step 1, and the ClO was used up in step 2. So ClO was the intermediate in this mechanism. And finally, we're asked to recall from our grade 11 chemistry classes that chlorine is normally a diatomic molecule. We normally write it as Cl2. But in this mechanism, we were dealing with something called a radical, a single chlorine atom. Write a balanced equation that could show how chlorine radicals might be removed from the atmosphere. So a simple thing to think of would be two chlorine atoms like this could collide with each other, and if they did, they'd form the Cl2 molecule. In doing so, we'd have less chlorine radicals in the atmosphere, and therefore ozone would be preserved. All right, in this next question, we're going to be looking at several different reaction mechanisms, and our job is to figure out the overall reaction, identify a catalyst, and identify intermediates if they exist. So in this first mechanism, you can pause the video and try it yourself. So canceling out things on both sides, I'm going to see the NO is a product in step 1, and the two NOs are reactants in step 2. If you're produced and then you're used up, you're an intermediate. I don't think there's anything else that cancels here. There's nothing else that appears on both sides of the mechanism, so there was no catalyst present. The overall reaction is whatever's left in the mechanism, so N2 reacts with two oxygen molecules, producing two NO2 molecules would be the overall reaction. Here's another one. You can pause the video and try that one yourself also. So we cross out, in this case, an oxygen atom produced in step 1, and then the oxygen atom used up in step 2. So an intermediate here is oxygen, produced and then used up. And there's nothing else that cancels out. So there's no catalysts in this mechanism. The overall reaction is whatever's left not crossed out. So what we have is an NO2 reacting with oxygen, and that produces an O and ozone. Here's a third example. So in this case, we can see the NO2 in step 1 is produced, and then it's used up as a reactant in step 2. So NO2 is an intermediate. We can also see here that the NO in step 1 is a reactant, but then it's a product in step 2. So that's the opposite situation. If you're a reactant and then later a product, you are a catalyst. I think that's all that cancels out. So the overall reaction is whatever's left. The ozone reacts with oxygen atom and produces two oxygen molecules. And one last example, a three-step reaction mechanism. So in this case, the N2O2 produced in step 1 is used up in step 2, so that qualifies as an intermediate. And also the N2O produced in step 2 is used up in step 3, so the N2O is another intermediate. There were two intermediates here. Are there any catalysts? Are there anything that begin as a reactant and then ends up as a product? I don't see that, so there's no catalyst in this mechanism. So the overall process, that whatever's left, two NOs react with two hydrogens, producing N2 and two water molecules. There's our overall reaction. All right. This next question shows us a potential energy diagram and then asks us several questions down below. So the first question we're being asked about is how many steps or how many collisions are in this mechanism. Well, we can see there's 1, 2, 3, 4 hills in the potential energy diagram. So because of that, there must be 4 steps in the reactions mechanism. Which step is the fastest? Well, to see that, we want to look at the activation energies for each step. So let me just sketch them here. In the first step, from the top of the hill down to where that hill began, about there, there's the EA for step 1. Step 2, from the top of that hill down to the beginning of that hill, there's the EA for step 2. And then step 3, from the top to where that hill began, the EA for step 3, and step 4 to where it began, there's step 4's EA. So which step was the fastest? It would be the step with the smallest activation energy. So in this case, it looks like the third step has the smallest activation energy. Which step is the slowest step? The rate determining step. Well, the slowest step has the largest activation energy. You could get a ruler, but it appears that the fourth step has the largest activation energy, so it's the slowest, it's the rate determining step. Which number, the 1, 2, 3, 4, all the way up to 9, represents a transition state in the first step? Recall that the transition state forms when the reactant particles collide, but they haven't yet become products. They're sometimes referred to as an activated complex also. So it forms, if we think of the reactants for step 1, they're here, and as those reactant particles collide, their energy increases to a maximum. So at 0.6 is where we have the transition state, or the activated complex, for step 1. So number 6 in the diagram represents that. Which numbers represent intermediates? Well, remember that the intermediates are the products of one step and they become reactants in another step. So number 2 represents the products in the first step. So the first step, there it is. Number 2 is the product of that step. But number 2 can also be thought of as the reactants in the second step. And as you go through the second step, you end over at number 3. So 2 was the product of step 1 and the reactant in step 2. Number 3 is the product of step 2, but it's also the reactant for step 3. So 2 and 3 qualify as intermediates. Number 4 is the product of the third step, but number 4 is also the reactants in the fourth step. So number 4 also qualifies as an intermediate. So the intermediates here would have been numbers 2, 3, and 4 in that potential energy diagram. Is the first step endothermic or exothermic? Well, to decide that, we're going to look at the difference in energy, the first step. So it started here with the reactants, and the first step ended here with these intermediates at number 2. So notice that the potential energy increases in that direction, so that means energy was being absorbed. If energy was being absorbed, it's an endothermic process, and the delta H for that, which is the difference between those two energies, the delta H for step 1, would have been a positive value. So the first step is endothermic. Energy was absorbed, delta H is positive. What does the number 1 represent in the diagram? Well, the number 1 is here at the beginning. As we can see, it's the reactants, the original reactants. Draw and label an arrow for the activation energy in the last step. Well, I've already done that. That would be EA number 4 over here, the last hill. And finally, draw an arrow for the heat of reaction, the delta H, in the last step. While looking at the last step, it begins at number 4 and it ends at number 5. So it's going down in energy, so its energy is being lost. It's an exothermic step. The difference between those two energies is the delta H for step 4. It would be a negative value. It would be an exothermic process. All right, we'll do one more question here together. So fill in step 2 of this mechanism, okay, and then we'll look at some true-false questions. So this gives us step 1 and step 3 of a reaction mechanism, and it also gives us the overall reaction. Can you use that to figure out what's missing in step 2? So what I usually do is first focus on things that are in step 1 or step 3 that aren't supposed to be there because they don't appear in the overall reaction. For example, the H in step 1 as a product is not in the overall reaction. So if it was a product in step 1, it's not a reactant in step 3, so the H would have to be a reactant in step 2, so that would cancel out. Is there anything else that's like that? While looking up above, we see the OH is a reactant in step 1, but it's also a product in step 3, so the OH cancels out. That's okay. Notice that step 3 has this HOO, and there's no HOO in the overall reaction. So the HOO is a reactant in step 3. The HOO would have to be a product in step 2 so that they canceled out. There's nothing else that falls into that category, so now is there anything in the overall reaction that doesn't appear in steps 1 or 3? So notice there's a CO in the overall process, but there was a CO as a reactant in step 1. There's an NO in the overall, and there's an NO in step 3 as a reactant. CO2 and NO2 are products overall, and they are products in step 1 and 3. But that leaves O2. O2 was a reactant in the overall, and there is no O2 in the mechanism, so we'll add the O2 as a reactant in step 2. So there's our missing step. O2 reacts with H and forms HOO. Now looking at the true-false questions, the first one says, true or false, HOO was an intermediate. Well, the HOO was a product in step 2, and it was a reactant in step 3. That is the definition of an intermediate, so that first statement is true. NO is a catalyst. Well, the NO is a reactant in the third step, but it's not a product in a later step. There is no later step, so that would be a false statement. Step 1 has the largest activation energy. Well, to decide that, we look on the right-hand side of the mechanism and we see those words slow, fast, and fast. Step 1 is described as slow. That means it had the largest activation energy, so that would be a true statement. And finally, OH is an intermediate. Well, the OH did indeed cancel out, but it began as a reactant in step 1, and it finished as a product in step 3. So that means it was not it was not an intermediate. That's false. It was in fact a catalyst instead. Okay. Now one last thing before we go, and this is a bit of vocabulary. So a reaction that occurs by a single step, so if the mechanism is a one-step process, that reaction is said to be an elementary reaction. And in addition, there's something that's referred to as the molecularity of a reaction or of a collision. It's determined by the number of reacting particles. So there's 3 different types of molecularity. If the chemical reaction has only one reactant particle, then that was a unimolecular step, a unimolecular process. If, on the other hand, there are 2 reacting particles, and they could be 2 of the same particles, or they could be two different particles. So if there are two reacting particles, that's a bimolecular step. If there are three reacting particles, and they could be all the same, they could be all different, there could be two of one and one of another. If there are three reacting particles, it's a termolecular step. Okay? You normally don't see anything beyond that simply because having more than three particles colliding in one step is very, very unlikely. On top of that, the particles would all need to have the right energy for the collision. That makes it even more unlikely. And finally, they'd all have to have the right geometry, the right orientation, and that makes the probability just so low when there's more than three particles that you really don't see that very often ever. So we deal with unimolecular processes, bimolecular processes, and termolecular processes almost exclusively, simply because the probability of four or more reacting particles in one step in an elementary process is just too low to be normally considered. So I'm going to pause and stop the video there. That's a quick introduction to reaction mechanisms. There's another video on my YouTube channel with more practice. You can watch that if you think you need a little bit more practice.